Hello everyone, and welcome back to another lecture video. In this lecture video, we're going to be discussing bar elements, which are sometimes called truss elements. It's used interchangeably. You guys have probably dealt with both scenarios, but in essence, they are the exact same type of element. Now, as you guys are going to see, these are perhaps the most simplistic elements when we're talking about the finite element method, but they provide a good starting point as the theory and the methodology we use to derive the equations we use for these elements is going to be the exact same as we'll use for other elements. So as this is the starting point for us in the finite element method, I find it's best to recap what we've actually done so far to kind of realize, all right, why do we need this finite element method? Well, when we started the course, we dealt with linear algebra. And we said, all right, well, linear algebra, it's not too much fun. No one really likes linear algebra, but it proved useful because it allowed us to derive a lot of the things that we used in solid mechanics. Now, solid mechanics was great because at the end of solid mechanics, we were actually able to derive a bunch of exact solutions for things like Euler-Bernoulli beams, beams under axial load, etc., etc. But then we said, oh, well, sometimes these exact solutions, they suck. And the reason why they suck is because they typically deal with solving a differential equation. None of us like solving a differential equation. So then we moved on to something called approximation methods, which provided us a way to approximate those exact solutions without the need of solving a differential equation. So basically, in general, we have learned how to solve for exact as well as approximate displacements of both beams and continuums. So let's say that I gave you guys the following cantilever beam here, subjected to a distributed load. You guys are all saying, Clayton, no problem. I can find the exact solution with ease, given I have the right computer software. And I said, well, you know what? I don't really want the exact solution. I want an approximation solution. And you guys are still laughing, saying, Clayton, no problem. Do you want the Rayleigh-Ritz method, or do you want the method of virtual work? I know both very well. I can solve for that approximate solution. So at this point, you guys are looking really great. But what happens if I give you guys a beam like this? Now, if we were to look at this beam, it's not too much different than the other beam with the fact that the cross-section changes throughout the length of the beam. Now this poses a bit of a problem because the moment of inertia, of course, will change with it. Remember that the moment of inertia is a cross-sectional property, so if the cross-section changes throughout the length of the beam, so will the moment of inertia. Now you guys may be saying, all right, Clayton, well, no problem. I can solve the beam using this equation, and I'll just take into the fact that the moment of inertia changes throughout the length of the beam. Well, that's actually a problem because this equation was actually derived under the assumption of constant moment of inertia. If our moment of inertia is changing throughout the length of the beam, the differential equation governing the behavior is also going to change. Now you guys may be saying, all right, Clay, I don't really care about that. I can go back and rederive it using a variable moment of inertia. But the point here is this. A lot of the things that we've assumed thus far, and there's a lot of them, well, it actually doesn't really hold true in reality. So some of the assumptions include linear elasticity. Well, of course, when we're dealing with things like concrete, we know that it doesn't behave linear elastic. We neglected Poisson effects, which in some cases can be quite significant. And one of the biggest ones, too, for Euler-Bernoulli beams is we assume that plane sections remain plane. Now, for those of you guys who have taken concrete design or anything like that, you know that this is particularly not true when we have the presence of a point load or a reaction or something like that. So the question becomes, all right, well, how can I effectively model all the things I want to model in reality while still maintaining appropriate accuracy? Well, the solution to this is actually the finite element method. So again, this was just a little recap. Why exactly do we need the finite element method? And now we're going to discuss the most simplistic form of the finite element method, at least in my opinion, and that is bar or truss elements. So to begin our finite element journey, we are going to start with these bar elements. And although they are the most simplistic, as you guys are going to see, they do a good job in capturing the methodology of the finite element method, which is going to be great because we're going to apply this exact same methodology for all the other elements we're going to encounter in this course. So let's say that I have the cantilever beam and it's subjected to an axially distributed load. Now what I'm actually going to do, and this is going to be one of the basis of the finite element methods, is instead of obtaining an exact or an approximate solution for the entire length of the beam, I'm going to discretize my beam into a series of nodes and elements. So I'm taking my big problem and I'm essentially making it into a series of smaller problems. Now you guys say, Clayton, what exactly are these nodes and what are these elements? Well, the yellow dots here, these are going to be the nodes. And this is actually where we're going to calculate the displacement of this beam. So before we calculate the displacement, or we'd approximate the displacement at every single point along this beam, but now we're only going to calculate that displacement at very specific points. So if we look here, we have 6 nodes, therefore we're actually going to calculate the displacement at actually 6 points along this beam. Now these nodes are actually connected by something called elements, so these would be the red lines here, and what we're going to do is we're going to take those nodal displacements that appear at the ends of the elements, and we are going to use that to approximate the displacement within the element itself. Now, again, a bar and truss element, they are the most simplistic because they are limited to axial displacement. Therefore, if I were to look at my element here, we know it can only be stretched or contracted in one direction. It's not going to shear, it's not going to bend or anything like that. So this is why it's the most simplistic. Now, if we look at it here, it also only has basically 2 loading scenarios. One is if we have concentrated loads at the nodes, so that would be F1 and F2, or 2, if we have a distributed axial load along the element, so that would be represented by P here. Now what we do is we say that this element actually has 2 degrees of freedom, because again we're calculating those displacements at the nodes. So if we were to look at this element, there's only 2 possible scenarios. One is the displacement of node 1, which I called U1, and the second is the displacement at node 2, which I called U2. So since we're only interested in the displacement of 2 nodes, we say that this actually has 2 degrees of freedom. And again, what we want to do is we want to calculate those nodal displacements, U1 and U2, and from that we can actually approximate the displacement along the element. So how do we do that? Well, we actually use our good old friend, the Galerkin method. So at the end of the approximation methods section, we briefly discussed what the Galerkin method is, and we said that this is the method that is most typically used in these finite element scenarios. So if you guys didn't quite understand it then, that's okay, because we're going to go into it in depth right now. So we're going to use this Galerkin method to derive basically 2 things. The stiffness matrix, which is going to be a matrix that relates those nodal displacements to the forces present at the nodes, and the second one's going to be the nodal force vector. And what that is if you guys remember, we had a scenario that we may have an axial load distributed along our element. Well, what we're going to do is we're going to take that axial load that's distributed along our elements, and we're going to convert it to 2 equivalent point loads located at our nodes. So that's going to be the goal here. So if we remember back to bars or trusses, they are governed by the following differential equation, where we have EA multiplied by the second derivative of our displacement function is equal to negative P, where A is the cross-sectional area and P is going to be that distributed load along our bar. Now what we're going to do, because we're doing the Galerkin method, is we are going to move all the terms to one side and call this our residual R. So our residual R, it's going to be the exact same thing, except all I'm going to do is I'm going to take that P and I'm simply going to move it over to the left-hand side. Now, recall that in the Galerkin method, we want the summation of the weighted residual error to be 0 over the domain. And you guys are saying, Clayton, those are just fancy words. What does that mean? Well, essentially what I want to do is I want to take the integral over the domain of our residual R, which we defined above, multiplied by something called Ni. And these are going to be called our shape functions. And these are going to be very special going on. And what I want is I want this integral to be equal to 0. Well, you're saying, all right, well, that's no problem because I know what R is. Therefore, I can substitute R into our equation. And again, we know it's going to be equal to 0. Now, for a bar, much like a beam, we know that the domain is simply going to be over the length of the beam. So that integral that was originally over the domain, well, I can simplify that as the integral over the length of the beam. So at this point, we're looking pretty good. We have our differential equations kind of substituted in. We know that we're integrating over the length of the beam, and we have something called a shape function, Ni, which we're going to discuss later. So now what I'm going to do is I'm going to say, all right, well, I'm going to take that P term, and now I'm going to switch it back to the other side. Therefore, I have 2 integral terms. Now I'm going to do something that everybody hates, all right? And that is integration by parts. So I'm going to take that term that was originally on our left-hand side, and I'm going to integrate it by parts to get the following uglier equation. You're saying, Clayton, why am I doing this? Well, this will be more apparent on the next slide. Now remember that this was just the left-hand side. So we took our left-hand side, which was originally that single term, and now we have 2 terms on our left-hand side. But of course we know that our left-hand side, well, that's going to be equal to our right-hand side. Therefore, we get the following equation. Now what I'm going to do is I'm going to say, all right, well, on the left-hand side now, I have a negative times the integral, and on the right-hand side, I have a negative times an integral. So I'm simply going to move those negative terms to the other side to make them positive, and I'm left with the following equation. Now this equation has something very special and that is this term right here. So if we were to actually look at this term, we see that we have the elastic modulus E multiplied by area, and then multiplied by the first derivative of our displacement function. Now we go, hold on one second, that first derivative of displacement, isn't that equal to strain? Well, of course. So this term right here, it's actually the concentrated loads at the nodes. Because if we take EA and multiply it by strain, we actually get a value of force. So these are actually going to be the forces that we apply at the nodes initially. Now, if you guys remember way back to the virtual work method, when we first derived our equations for Euler-Bernoulli beams, we had shear terms and moment terms. And we said, well, this is actually really gross. I don't want to find the shear. I don't want to find the moment. And what we were actually able to do is simplify it to the idea that the only time those terms apply is when we have externally applied concentrated loads or concentrated moments. And the same thing applies right here, is this term will only be non-zero if we have an externally applied concentrated load at our nodes. Now what happens is if we were to just leave it in here, it's going to be equal to 0, but we still have to account for that calculation over and over again. And when you guys deal with very large scale problems, when you guys are dealing with maybe say 1,000 elements, well, you guys don't want the computer to be wasting computation time to keep calculating this again and again and again. So what we're actually going to do is we're going to say that this is going to be accounted for separately. What does this mean? Well, if I look at my equation above, I'm just going to take it out of my equation. And if I'm dealing with my problem and I have those concentrated loads at the nodes, well, I'm just going to tack them on appropriately. I'm not going to keep calculating it over and over and over again. Now from this, we get the following equation, where we have the integral over the length of the beam of EA multiplied by the first derivative of our displacement function, multiplied by the derivative of our shape function, is equal to the integral over the length of the beam of our distributed load multiplied by our shape function. So if we were to look at this, we say, well, I know what EA is, the length of the beam, L, that's just the length of the beam. The displacement function, that's again, no problem, I'm familiar with that. So the only really question that we have here is, what exactly is this shape function Ni? Well, as you guys are going to see, the shape function can actually vary depending on the geometric order of the element. So you guys are going to hear that term a lot, geometric order, because as we're going to see, the geometric order is related to the shape function that we assume. So if I were to have an element here where the left-hand node is located at a distance x1 and the right-hand node is located at a distance x2, we said that what we're actually trying to get here are these nodal displacements. So we're trying to find u1 as well as u2. But keep in mind that we said that once we know those nodal displacements, we are actually going to use them to approximate the displacement within the element. So the first type of element we are going to discuss is called a linear element. And what this means is that we're going to approximate that displacement solution throughout the element as a linear equation. So my displacement through the element, UE, is going to be equal to A0 plus A1 times x1. So this is when it's going to start looking real familiar to things like the Rayleigh-Ritz method or method of virtual work, and the fact that we now have an approximate displacement function, and it has those A coefficients that we love so much. But then we're going to say, well, hold on one second. I don't know what A0 and A1 are, and frankly, I don't care. Remember that we want to express this displacement function in terms of the nodal displacements, U1 and U2. So what we're going to do is we're going to take this approximation function, which is currently a function of A, and we're going to want to replace it so that it's a function of those nodal displacements U1 and U2. Well, this is actually pretty simple because all we need to do is substitute our values into our equation. So at the left-hand side, we're going to substitute a value of x1. So we get A0 plus A1 times x1, and we know that this is going to be equal to our nodal displacement U1. And the same thing for the right-hand node, x2. So I'm going to have A0 plus A1 times x2, and this is going to be equal to the nodal displacement U2. From this, I have two equations with two unknowns, A0 and A1. Therefore, I can simplify this equation and determine what A0 and A1 are equal to. From there, I'm going to take these values of A0 and A1, and I'm going to substitute them into our original approximation function. So remember that we had A0 plus A1 times x1. Well, I just took A0 and A1 and I substitute them in here. Now I'm going to do something a little bit fun. We're going to rearrange this equation so that we now have a function times our nodal displacement U1 plus a function times our nodal displacement U2. And if you guys remember back to the Galerkin method, this follows exactly what we defined our approximation solution as, where we have some constant, in this case it's U1 and U2, multiplied by some trial function, phi1 and phi2. Now in this particular case, we're going to call that trial function, phi1 and phi2, as our shape function. So those coefficients in front of u1 and u2, those are actually going to be our shape functions, n1 and n2. So every time you guys hear me say shape functions, you guys now know exactly what I'm referring to. And you guys may be saying, all right, well, Clayton, what exactly does this shape function n1 and n2 represent? Well, if we were to look at our element right here and we were to plot n1, it's simply the linear equation that starts at u1 and goes down to 0 at the other node. And similarly, if I were to look at n2, it starts at 0 at x1 and it goes up linearly to achieve u2. So one of the fun things about these shape functions is they have some specific values, which is always nice. The shape function at its own node, so n2 and node 2, it's going to be equal to 1. So if we were to look at our shape function n2, and we were to calculate it at the node u2, it'll have a value of 1. Now if we were to calculate n2 at node 1, it would actually have a value of 0. And this is going to be one of those fun little parameters that we're going to play around with later on. So similarly for n1, it's going to have a value of 1 at node 1, and it's going to have a value of 0 at node 2. So we're going to say, all right, well, now that I know what these shape functions are, we can now play around with that expression that we had. Remember, we had that expression. We said, well, we basically know everything in there besides what those shape functions are. So we're going to go back to our expression. And now that we know our shape functions n1 and n2, let's see what we can do with it. And the first thing we're going to look at is that displacement term. So we're going to look at the first derivative, du, with respect to x1. And we're going to recall that our approximation function, as we defined in the previous slide, is simply a linear combination of the nodal displacements and the shape functions. What does this mean? Well, our approximation here, u, is simply u1 times our shape function n1 plus u2 times our shape function n2. And now we're going to take a step back and say, well, hold on one second. u1 and u2, those are our nodal displacements. So those are actually just constant values. It's the displacement at node 1 and it's the displacement at node 2. Therefore, if I were to take the derivative of this approximation function, u1 and u2 are constant, so they don't really apply. So the derivative of our displacement function with respect to x1 is simply going to be u1 multiplied by the derivative of n1 with respect to x1 plus u2 multiplied by the derivative of n2 with respect to x1. Now I'm going to do something that all you guys will hate, and I'm going to represent this in more of a vector format. So our derivative of our displacement function u with respect to x1 is going to be the vector dn1 with respect to x1, dn2 with respect to x1, and then multiplied by the vector u1, u2. So what I'm going to do is I'm going to take that nice vector format and I'm going to substitute it into our expression right here. And by this point, we're actually good to go. So the first thing I really want to emphasize is that when we look at this expression, I took that nodal displacement vector, u1 and u2, and I moved it outside of the integral. Why did I do this? Well, it's constant. Remember that those nodal displacements, they're constant. Therefore, when I take the derivative of them, or if I integrate them, well, they're just constant. So I don't really need to include them within the expression. Now, if we were to take a step back, we basically have something times our nodal displacements is equal to something. So what those somethings are is the first one on the left-hand side is called our stiffness matrix. Okay, so this term that we have right there, that's going to be our stiffness matrix. And on the right-hand side, we have what we call our nodal forces. So if we were to take an even further step back, we basically have something times displacement is equal to forces. And this is exactly what we want. And this is how we're actually going to solve for our nodal displacements. Now, another thing I really want to emphasize, and this is where students will start getting lost, is this expression right here. It's actually two equations. It's not just a single expression or one equation. It's actually two equations. And the reason why is if we look in this expression, we have the term ni, which means our shape functions. And since we have two shape functions, we have two equations. And this will be more apparent on the next slide. So let's say that we want to examine what our stiffness matrix will be if EA is constant. Well, remember that we have this nice equation for our stiffness matrix here, and we basically need to determine two things before we can plug or chug our way through. We see that we need to take the derivative of n1, and we need to take the derivative of n2. Well, we know our shape functions. They're simply x2 minus x1 divided by L, and x1 minus x1 divided by L. So keep in mind that the small x there, those are the nodal coordinates, okay? Those aren't some sort of variable like big X1. Those are the nodal coordinates of our element. So from here, if we look up at the first one, and we were to take the derivative of n1 with respect to x1, well, it's simple. It's just negative 1 over L. And same thing for the bottom. If I were to take the derivative of n2 with respect to x1, I simply get 1 over L. So it actually looks really complicated, but it's actually really, really simple, which is great for us. We love simplicity. Everybody likes things nice and simple, and that's what we're trying to do here. So remember that this equation above is actually two equations, which sounds kind of funny. The equation above is actually two equations, but now we'll see why. So our first equation here, we're going to substitute our first shape function. So when I have that dni with respect to x1 term, well, ni in this case is going to be equal to n1. And we know that the derivative of n1 with respect to x1 is simply negative 1 over L. So that's why I have it in there. Now this is going to be equal to EA divided by L, and then the vector 1, negative 1. Similarly, I'm going to move on to my second equation, and instead of taking the derivative of n1, now I take the derivative of n2, our second shape function, which gives me 1 over L in this expression. From here, we can solve, and we get EA divided by L, and then the vector negative 1, 1. So we can conclude that the stiffness matrix for a linear bar or truss element is simply going to be EA divided by L, and then the matrix 1, negative 1, and 1. So if you guys have taken any sort of structural analysis, this is exactly what you guys would have derived, and this should be familiar to most of you. However, when we came to structural analysis, this is where we would stop. We say that we have this nice stiffness matrix here, we're good to go. Well, in finite element method, we're actually going to take it a step further, and we're going to look at something called quadratic elements. So this is where it's going to start to confuse a lot of students. So I'm going to take it a little bit slower, and hopefully we can emphasize some things. So for linear elements, we had one node at each end of the element. And we said that both of these nodes have a corresponding nodal displacement, in this case u1 and u3. So this is what you guys are used to. Nodes only appearing at the ends of the element. Well, for quadratic elements, we actually have a third node, and this node is located in the middle of the element. So I put it's located at x2, but it's actually located in between x1 and x3, directly between x1 and x3. So this node will also have an associated nodal displacement u2. And in this particular case, we are approximating the displacement throughout the element as a quadratic polynomial. So before we did a linear approximation, now we're doing a quadratic approximation. So before we had a0 plus a1 times x1, but now we're including an a2 times x1 squared term. So again, I really want to emphasize this because this is the thing I find most students tend to have trouble comprehending, is that even though we have three nodes here, this is still only one single element. So three nodes for one element, which again confuses a lot of students. They're so used to linear elements that when they look at this, they think it's actually two elements, but no, this is just one single element. Now, if you guys can kind of understand that this is one single element, well, the rest actually goes pretty smooth because the process is going to be the exact same. Right now, we have an equation in terms of a0, a1, and a2, but we don't want that. We want it in terms of our nodal displacements, u1, u2, and u3. So again, just like before. How do we do this? Well, we're going to solve for a0, a1, and a2 using those nodal displacements. So again, exact same process as before, only this time the solution gets a little bit messier. However, using some computer assistance, we can figure out what our three shape functions are. So in this case, we see that we have three shape functions, n1, n2, and n3. Now, again, I said that this becomes really, really messy. So the key here, again, I just really want to emphasize, three nodes for one element. And because we have three nodes, we now have three shape functions. And if I were to look at these shape functions, we see that we have n1 times u1, we have n3 times u3, and then we have n2 times u2. So each one of these shape functions is now a parabola rather than just a linear function. So the question becomes, all right, well, how do I attain the stiffness matrix for these quadratic elements? Well, we're going to do the same thing where we're going to take our equation and we're just going to substitute the values of ni. But before we do that, we look at that derivative of our displacement function, and we're going to try and derive an expression from that. Just like before, we know that this displacement function is going to be a linear combination of our nodal displacements and our shape functions. Therefore, u is equal to u1 times n1 plus u2 times n2 plus u3 times n3. And just like before, yet again, those nodal displacements are going to be constant. Therefore, we can simplify the derivative of our displacement function into as follows. So this is why I like starting off here, because if we get the basics of a linear element, well, quadratic elements, again, it's the exact same steps. So when we move to our final expression, as we can see, it's the exact same final expression for linear elements. The only difference is we now have 3 components in our vector there rather than 2. And the reason why is because we have that additional node that we need to account for. So before we had dn1, dn2, as well as u1, u2. Well, now we have dn1, dn2, dn3, as well as u1, u2, and u3. But again, the exact same thing. We say that the term in front of our displacement vector is our stiffness matrix, and the term on the other side is our nodal forces vector. Now in this case, instead of 2 equations, we actually have 3 equations because we have 3 different shape functions. But again, everything else is the exact same. So let's say that we had a stiffness matrix with a constant EA, and x1 is equal to 0 and x3 is equal to L. Now remember that that middle node, which we called x2, that is directly between x1 and x3. Therefore, that would have a value of L over 2. So if we were to take this equation, all we're going to do is we're going to say, all right, I need to take the derivative of all 3 of our shape functions. Therefore, we get the following. Again, it looks a lot uglier than it did before. So remember that this is actually 3 equations, and all we're going to do is we're going to substitute the derivative of each one of these shape functions into our equations to obtain our 3 equations. So our first equation right here, where that n term is dn1 with respect to x1, our second equation where the n term is dn2 with respect to x1, and our third equation where the final term is dn3 with respect to x1. So again, I'm just going to solve those 3 equations, and I obtain my stiffness matrix as EA divided by 3L, and then the matrix 7, negative 8, and 1, negative 8, 16, negative 8, and 1, negative 8, and 7. So if you guys remember back from the linear elements, we're going to see some similarities start to pop up. And the first is this. When we're dealing with these nice linear elastic elements, our stiffness matrices are all symmetrical. So that's one of the little fun facts that we can use to our advantage and help reduce computation time. So before it was 1, negative 1, and then negative 1, 1. That's symmetric. If we look here, the 7, negative 8, and 1, negative 8, 16, negative 8, 1, negative 8, and 7. Again, that's nice and symmetric. So we now have our stiffness matrices for our elements. So the last thing I just want to touch up upon is this. We just calculated 2 different stiffness matrices for the exact same elements. Remember, we're still dealing with these bar and truss elements. The only difference between these 2 stiffness matrices has to do with the geometric order of the element. So we dealt with 2 different geometric orders. The first one is linear, and then the second one is quadratic. Now, if we compare the 2 stiffness matrices, we see that the linear stiffness matrix is much smaller than the quadratic. It's 2 by 2. However, the quadratic stiffness matrix is 3 by 3. So the question is, well, what are we getting if we switch from a linear to a quadratic element? Well, remember the approximation function for the elements. So the nodal displacements, those will always be the same no matter if you're doing a linear or a quadratic element. However, these quadratic elements include that additional node, and the approximation function used is quadratic polynomial. Therefore, the accuracy between the nodes will be much better than a linear element. But of course, if we look at the quadratic element, it has a larger stiffness matrix, therefore more computation time. So the question for you guys is going to be, should I use a lot of linear elements or should I use fewer quadratic elements? As you want to try and find a nice balance between the accuracy of the solution and computational expense. So now we're going to move on to kind of a more general concept called our element stiffness, which is also termed our local stiffness, and our global stiffness. So what we just derived was what we called the stiffness matrix of the element, and this is called our local stiffness matrix. However, in most scenarios when we're dealing with the finite element method, we don't just use a single element, we have a collection of elements. So the stiffness matrix of the element is going to be different than the stiffness matrix of the structure. However, we can use these local stiffness matrices to construct this stiffness matrix for the entire structure, and that stiffness matrix for the entire structure is actually called our global stiffness matrix. So our global stiffness matrix, which I call big K, is simply going to be a collection of our local stiffness matrices, KE. Now, and if you guys look in textbooks, they may call these stiffness matrices a different thing. This is just how I personally call it. Really up to you. You guys are going to be the one programming it, so whatever you guys want to call it. Now, To get this global stiffness matrix, we simply add the stiffness coefficients of the local matrix to the global matrix based on degrees of freedom. Now you guys are saying, Clayton, what the hell did you just say there? That makes no sense. Well, I agree. It doesn't make any sense, and it's not something I can really write down and show you guys. So the best way to me is to show you guys an example. So let's say that we had this beam here, and it's composed of two linear elements. So two linear elements, therefore we have the three nodes, node 1, node 2, and node 3. And we know that from our previous derivations that the stiffness matrix of that first element, so between nodes 1 and 2, is simply EA divided by L, and then the matrix 1, negative 1, negative 1, and 1. Now, if we were to look at this matrix in terms of our global structure, we know that this stiffness matrix is related to degrees of freedom 1 and 2 because it's between nodes 1 and 2. Therefore, I can actually index this local stiffness matrix as 1, 2, and 1, 2. Now, if we were to move on to the other side, so our second element, which is between nodes 2 and 3, we can derive a second local stiffness matrix, which is EA divided by L, and then 1, negative 1, negative 1, and 1. And we can actually relate this local stiffness matrix to the degrees of freedom of the entire structure. So since this matrix is between nodes 2 and 3, we can actually index this matrix 2, 3, 2, 3. So in general, these degrees of freedom correspond to the index of the global stiffness matrix. Now you guys may be saying, Clayton, what exactly do you mean by that? Well, if we look at this structure as a whole, we can tell that it has 3 degrees of freedom as a whole. Therefore, our global stiffness matrix is actually going to be a 3 by 3 matrix. And what we're going to do is we're going to take the indices of our local stiffness matrix and substitute them into our global stiffness matrix. So K here is actually going to be EA, and then the matrix 1, negative 1, and 0, negative 1, 1, and 0, and then 0, 0, 0, which corresponds to that first element right there, plus EA divided by L, 0, 0, 0, 0, 1, negative 1, 0, negative 1, and 1, which corresponds to our second element over on the other side. So if we were to look at our second element, we can see that our second element doesn't touch node 1 whatsoever. Therefore, all the entries in our global stiffness matrix related to 1 are actually all equal to 0. Therefore, the global stiffness matrix of this bar as a whole is simply EA divided by L, 1, negative 1, 0, negative 1, 2, negative 1, and 0, negative 1, and 1. Now this is, again, very hard to describe, so I hope by the end of this you guys know what I'm trying to say. So the last thing that we're going to do is actually solve our system. So let's say that we want to solve the following system with two linear elements. All right, well, we said before that our global stiffness matrix for this particular case is EA divided by L, 1, negative 1, 0, negative 1, 2, negative 1, and 0, negative 1, and 1. We know that we want to solve for the nodal displacements U1, U2, and U3, which are the displacements at each one of those nodes represented by those yellow circles. Finally, we also have our nodal forces vector. Now, our nodal forces vector is actually composed of two things. The first one is our nodal forces vector that we solved for, which came from the integral of P times Ni. Now, what this essentially accounts for is the distributed loads. So these are the loads between the two elements. Now, our second term over here, which we talked about before, was that term that was related to the concentrated loads applied at each one of the nodes. Remember that in our derivation, we canceled it out because we said, well, basically, we're calculating something that's going to be equal to 0 unless a very specific case happens. So we said that we're going to account for it separately, and that's when we do is right now. So what I did was I took our nodal forces vector, and I'm adding it to any concentrated nodes. Now, in our particular scenario right here, we see that we have no distributed loads, so therefore Fn1, Fn2, and Fn3 are all going to be equal to 0. But when we start looking at our concentrated loads, we can see that at the very left-hand side, node 1, well, there's going to be a reaction force there. So we're going to call that R1, and we don't know what that is. Our middle node has no concentrated loads, so it's going to be 0. And then our third node at the other end has a load P, so we're going to call that P. Therefore, our total nodal forces vector is going to be R1, 0, and P. Now, I know you guys know what R1 is equal to. It's very, very, very obvious. However, in the most general sense, we don't know what those reactions are, especially if we're dealing with indeterminate systems. So that's something I want you guys to keep in mind. But if we were to look back, we say, all right, well, we know that we have a linear system where our stiffness matrix multiplied by our nodal displacements is going to be equal to our force vector, and we can start substituting all the values in to get the following. Now, this is where it comes in the fact that we may not know what that reaction force is. Again, you guys have to humor me because in this scenario, you guys are going to say, Clayton, it's obvious it's going to be equal to P. But again, sometimes we may have indeterminate systems and we actually don't know what R1 is equal to. Therefore, in general, we have unknowns on both sides. Remember, we don't know those nodal displacements and we don't know that reaction force. If you guys remember in the Galerkin method, I said that if we don't include that boundary condition, we get infinite solutions. Well, in a mathematical representation, this is why we have those infinite solutions, because we're dealing with this right here. So what we're actually going to have to do is we're going to have to utilize the fact that we know that U1 is equal to 0. Therefore, all the entries with 1 in it, we can just neglect. So therefore, our new matrix actually becomes the following right here, where we have EA divided by L, and then the matrix 2, -1, -1, and 1, times the displacement vector U2, U3 is equal to our force vector 0P. Now in this particular case, the only unknowns that we have are U2 and U3. Therefore, we can solve for U2 and U3 using those nice linear operations. Now what's nice too is because since we know that U1 is equal to 0, and we now know U2 and U3, we can actually go back to our original matrix that we had above here, and our only unknown is actually going to be that reaction force R1. So if we wanted to, we can actually back calculate and figure out what R1 is equal to. But the nicer thing that we have to realize too is now that we know all the nodal displacements, U1, U2, and U3, we can actually determine our approximation functions or our displacements within the elements themselves. And if we know the displacements over the elements, for instance, if I were to know the approximate displacement function in one of the elements, I can now take the derivative of that approximate displacement function to give me the approximate strain distribution. And if I know the material behavior, I can take that strain distribution and convert it into a stress distribution. We're going to talk more about that once we start talking about quadrilateral elements. But that's a different lecture. So that's it for this video where we discussed bars and truss elements. Thank you guys so much for listening. I really appreciate it. I hope I was able to provide some clarity on these truss or bar elements, and if not, then I'm sorry for wasting your time. So again, thank you guys so much for listening. I really appreciate it. I will see you guys in the next lecture video.